Hello everyone and welcome to this next lecture on Python Power Electronics, and this will be the last and probably the concluding lecture on how to write control functions using Python Power Electronics. So as always, I will come to my website pythonpowerelectronics.com and I go to the download section. In that I check out papers and I just open up controlstructure.pdf. This is just for ready reference. So I have covered almost every aspect of how to write control functions. There's one which is left, and that is output. So in this I'm going to talk about output, and I will just describe how we can write controls in a slightly better manner. So with this done, let's start off the simulator. So I go into my virtual environment. I activate my virtual environment and I just have to check the version of Python. That's it. So now I'm starting off the simulator. And the simulator is finally running. This has been something which I've been doing in almost every lecture. This is pretty much the same with everything else. I'm just going to go launch the simulator, go to simulation library and load the simulation. So I'll quickly zip through these parts. You just have to edit, go back to main page, add circuit, process circuit schematics as always. No errors have been detected. Go back to main page, edit circuit parameters, nothing here to do. Now finally I come to edit control. So now in this control, in this simulation, let me just go back and open the circuit file. So in this simulation there is only one controllable element, and that is in the load. It's basically a switched load. So what we're going to do is I'm going to tell you how we can control this switched load. So let me open this. And this is the load. So there are two loads. One is resistor load 1, which is a static constant load, and the other is load 2, which is a switched load. So there's a switch in series. So up till now the switch has always been open because we've never done any control, and the switch is by default open. Now we're going to have to control the switch, and this is pretty similar to most of what we've done before. So let's go back to our simulator, and one simple way to do this is, let me just quickly, let me remove this control file and let me add another one. Let me create an empty file and I will call this gating control. So this is a file which I'm creating and is brand new, and I'm here going to control the output to that switch. Alright, so now that I have created this, I can always go to the simulator and add this file. So let me go here and add gatingcontrol.py. Now I'm going to build this up bit by bit. So first I'm just going to create a basic control, just tell you how it works, and then I'm going to go and refine this a little and tell you how you can actually create something like a pulse width modulated control. So let me write this control file for generating gate signals to switch. Alright, just a basic description. You can write whatever you want. Do not forget to click save control. So now it's been configured. So now that we have this, let me go and configure this. Now I could add very similar outputs to all these, but here I am looking at only one particular, or rather two of them. One is control output. So now let's go back to this data sheet, or rather data sheet is here. Now let's look at how the output is. You see what's happening here. The output has to be an element in the circuit spreadsheet. Alright, like I said in the previous lecture, even if you're connecting two control files together, the output cannot be from one control to the other. The output of a control file has to go to a controllable element. If you want to connect two control functions together, you have to use variable storage. You cannot use input output. Input means from a meter, output means to a controllable element. So now we have to specify which control element will take this output, and we have to specify a variable name that we will use in the control function. Okay, sorry, this is the one, desired variable name and control code, and we have to give it an initial value. So let me show you how that works here. Let me add this value. So what is the value that I want to give? Let me call this switch gate. Okay, that's fair enough. Initial value, let's say 0.0. Now remember something, this switch, if it has a gate signal of 0, it is off. If it has a gate signal of 1, it is on. That's how it works. Okay, that's how it works. Now you see here the drop down shows only 1 because there is only one controllable element, and in future lectures when I actually describe the control of more complex converters, you will see there will be several switches or several other elements which can be controlled. So let me save this. That's all we have. Now just this is enough to actually have this thing going, and I'm going to show you how that works. Now that we have this, or rather let's not throw it away, let me go and write this. So I'm going to write a very simple control. All right, I'm going to say if t clock, or rather let me go and define also a time event variable. Let me define a time event. So let's give this gate time interval. So I'm defining a time event variable for this control file, all right, so that I have some control over how this works, because otherwise it won't be very convenient in actually seeing the output. So let me save this time event and let me now use this. So first what we're going to say is if t clock is greater than or equal to, let me copy this variable so that I don't make a mistake in the syntax. Okay, if it is, then what am I going to say is, I'm going to say if, let me use the variable itself. The variable is switch gate. What this means is the variable name in control code, the output target. These two are connected. All right, if you assign any value to this variable, any value at all, that immediately gets transferred to this control element. Okay, you don't have to do it, the simulator does it. At the same time, you can also read this. That's not a problem. In some simulation software, you cannot read the value of an output. All right, that is a syntax error. That's not the case here. In this case, you are very welcome to read the switch gate. You are very welcome to read the value of the output. So we can use this value and say if switch gate is equal to 0.0, that means if the switch is off, we turn it on, and we say 0.0. So all we say is we are toggling the switch. If switch gate is 0, if the switch is off, you switch it on. If it is on, that is if it is else, you switch it off. Okay, and as always, there's something you need to remember. Do not forget to update your time event variable. Do not forget this. So what value should we give? Let's give it a value of 10 millisecond. All right, so we are toggling the switch every 10 milliseconds. So this is all we need to do. This is all we need to do to design the control. Why? Because we have said we have defined in this simulator interface that this any variable that this variable switch gate is connected to the controlled element. So we can read the value of this controlled element and we can write a value into this element, no problem. Okay, if you write a value into the switch gate, it gets automatically transferred to the gate of the switch. So by saying switch gate is equal to 1, you are turning on the switch. By saying switch gate is equal to 0.0, you are switching off the gate. You're turning off the switch. So now, to make this a little obvious, let me just go back and edit the circuit file. You know what I'm going to do? The reason I'm going to edit this is because the existing load is huge. Okay, this resistor, for example, let me go back here and show you. There are two resistors, load 1, load 2. Okay, now the present load, that is load 1, is 10 ohms. 10 ohms is a very small resistor, and that's the reason why we are seeing such huge jumps. So let's increase this to 50 ohms. Okay, and let us say that this resistor load R2, okay, let me come here, resistor load R2 is a switch load. Let's also make that 50 ohms. Now, the reason why I'm doing this is now when the switch turns on, your load doubles, your load current essentially doubles. So we'll be able to see that. So let's do that. So we go back to the circuit list, go back to main page, and I think we are more or less done. We can run the simulation. So as usual, I click on run. Simulation is running, but as always, go here and you see there is an error. So I made a very stupid syntax error here. This is not how you write Python code. So let's go back. Well, no matter how much you use a software, you're always likely to make some mistake. All right. Remember, when you're doing a conditional check, it's always equal to equal to. So this is a mistake. Let me go back and let me run this. Okay, let me see, simulation is running, and this time there's no error. So that's it. That was just a stupid silly mistake which I made. So now let's go back and let me plot. What plot should I plot? Let me plot this IS and IL. Okay, it is plotted, and that comes in current plot. So let me open current plot. So it's still 2 because it hasn't run enough, so I have to let it run for a while. Because what has happened is, you see the orange line. The orange line is the load current, but the load current will show a jump only after 10 milliseconds because that's the amount of gap I've given. So I guess we could change it. Maybe I'll change it in the next simulation run. But we would just keep plotting it and we should see a change. Yeah, so now you're seeing a change. Oh no, actually this is a change within. It's still only for 4 milliseconds. Actually, this is a wrong plot. The reason why we didn't see it is because the load current is not into the load current is not a part of the entire topic, which is why we are not seeing this. Okay, let me just replot this. Okay, I'll tell you what the mistake was, and it actually is a mistake in the circuit. What I was plotting is, I am plotting this load current. All right, that's what I'm plotting as load current. but this load current only measures the resistive load, which is never changing, so which is why you'll never see a change here. To bring in a change into this, I'll have to put a resistor somewhere here. Now that is a challenge, because you see the mistake which I made. I have put them all very close. So how do I change this? I will have to change this in a slightly subtle manner. What I will say is, and this is usually circuit diagram, like even I said, always spread out your circuits, like spread these out as much as possible. Now there is another way to do it. I am going to go into the diode rectifier, alright, and I will add an ammeter here. Now usually this is bad design, and I would suggest the only way to really avoid this kind of mistake is to spread out your circuits as possible. Try to leave at least 2 or 3 cells, because then what happens, you can insert values into this, because when you squeeze it in like this, I can't add an ammeter anywhere, you see, because you can't add an ammeter just next to a node. So that's the reason why. And because not only can you not add an ammeter has to have a resistor in series. So that's the reason why this is a problem. So what I'm going to do is I'm going to say ammeter direct 1 output. Then I'm going to add a resistor in series, direct 1 output. Okay, and let's just insert another column here, just for cleanliness, just for neatness. Okay, so let me go back. Now remember, when you make a change in the circuit, you have to go back and you have to process the circuit schematic. I am not changing the name, so I don't have to go and change these files. Okay, they are already entered, but I have to click on process circuit schematics, because process circuit schematics is necessary to make sure that any change you make in the circuit does not create an error. So let's come back and see. It says circuit does not have any detectable errors, so we are good to go. So now that we have done this, we added circuit file. Now I have changed DREC. To change DREC, I now have to go to that file, that is the resistor direct 1 output. This is a parasitic resistance, so we can just make it 0.01 and save it. And the ammeter 1K going to 1J. Let's look at it. The ammeter is at 1K and the positive direction is towards 1J. Well, that's not exactly what we want, because the positive direction should be 1L. So let's change that also. So I will change that to 1L, save parameters. Go back to the circuit list, back to main page, and now I can run it. So what I'm going to do is I'm going to create another plot, because this plot does not have that. So let me add another plot with this latest variable that we have. Add plot, and let's call this output current plot. Start plot. Let's add the waveform. We can add the source current. We can add the load current. Now, which load current are we going to add? We are not going to add load 1, because load 1 does not measure the current drawn by the switched load. So we are going to add direct 1 output, because direct 1 output measures the combined output of both loads. So let's do that, and let's call this I out. Save waveform, and I think we are done for now. So let's save this plot. So now that we are done with this, let's plot this value. Okay, let's check what has been plotted. So now we have to look for output current plot. So this is the output current plot. Now it may seem a little complicated. The reason is because we are not measuring the output across the capacitor. That's why it seems confusing. You see, there are two here. There is the source current and then there is the load current. All right, the source current is the same as the load current during the positive half cycle, because remember the output current is always unidirectional because it's the output of the diode rectifier. Let's go back and I'll show you. You see this ammeter, the current is only going to flow in this direction. It will only flow from K towards LM. It can never flow back in here. All right, so the current will always measure a positive value, but the source current will have a positive value and a negative value. So you see, during the negative half cycle, the source current is negative, but the output current is still positive. During the positive half cycle, they are merged together. That's why you don't see a blue line here. You see, they are the same. But what's important, you see the magnitude. The magnitude during one cycle is double the magnitude during the other cycle. Let me plot it again because more plots would have generated, more waveforms are generated. So let me plot it again. It's data page. Let me show you what it is. Yeah, and you see the same pattern is being repeated all over the time. You see, every time, you see at every 10 milliseconds, it's like 0.06, this is 0.07, it's double the value. 0.08, double the, again half the value. So you see, this switched waveform has produced this switched output in this entire simulation. So typically you wouldn't use a switch in this manner. You would use a switch in a converter, you would switch in a buck converter, and I'll show you these examples at a later stage. This is just to show you how the output can be configured. Now that we have done this, I want to take some time to tell you how you can actually do a slightly more complex control. Again, it does not mean anything here simply because the control we are doing is so minimal. But I would still like to show you exactly what are the capabilities of this. So the first and foremost, we have done this control. Okay, what I would like to show you is another thing. I would like to show you how you can do a pulse width modulation. Now, what is pulse width modulation? Pulse width modulation means you're comparing a modulation signal with a sawtooth waveform. All right, it can be a sawtooth waveform, can be a triangular waveform. A triangular waveform is what is used in a DC to AC converter. Here we have a DC system. At least the switch part is in the DC part of the system. So we don't need a triangular waveform, we need a sawtooth waveform. So let me go and tell you how the sawtooth waveform is generated. First and foremost, let me take the frequency of the sawtooth. Let me call this FSW. This is a initial variable. So let's give it 1000 hertz. Okay, so the time period of this is going to be 1 by FSW. So FSW is the frequency of the sawtooth waveform. TSW is the time period of the sawtooth waveform. Now, the reason I want to also show you this is because I believe this is not very easy to understand. Now, in a simulation, we have the simulation time instant. The simulation time instant is the time step of your integration, rather the simulation time step. In this simulation, it is 1 microsecond. Now, usually you will run your control at a much slower rate. Most DSPs will run in milliseconds or maybe hundreds of microseconds. Typically, you do not run a control faster than your simulation time step because it doesn't make much sense. But there are certain cases, and one of those cases is in the case of things like pulse width modulation. Now, if you look at your digital signal processor and you look at your hardware specifications, the resolution of your pulse width modulation is quite often in nanoseconds. For example, I'll just comment this and write pulse width modulation resolution is, let's say, 10 nanoseconds. Okay, now you want to mimic this in your simulator because you want to know exactly how your digital signal processor will work and how your converter will work when you fire it with a digital signal processor. So what do? You need to have a 10 millisecond resolution to a control signal. Now the question you might ask is, my simulation time step is 1 microsecond. So how is my control less than my simulation, right? How can my control be faster than the simulation? That's what you might think. Actually, in this circuit simulator, Python Power Electronics, that is possible. Your control sampling time period can be faster than the simulation time step. Now, for details on this, I would suggest read this paper, Time Scheduler. The timing scheduler tells you the concept of how control functions are timed and how the simulation runs. So there is a concept of a time event. All right, I won't talk about it here. It's fairly complex and I don't want to take too much time, but this tells you exactly how this scheduling takes place. So I would suggest you read that paper, but here I need to tell you that it is possible to make this 10 nanoseconds. All right, so therefore this control function is going to run faster than my simulation. All right, sounds actually unthinkable, but it is possible. Now there is something else we need to generate the Sawtooth waveform. What is a Sawtooth waveform? Sawtooth waveform starts at 0, goes up to 1, all right, in the time period TSW. That's what it is. So basically it has a slope of 1 divided by TSW, because 1 is the magnitude of the sawtooth and TSW is the time period in which it goes from 0 to 1, right? So 1 by TSW is actually FSW. All right, so we don't even have to do this. So all you have to do is you have to say carrier wave plus equal to FSW multiplied by this time. So now let me give it a time. I shall call this dt. This is the time period of this is the time step of this control. So now that I have defined it on top, I can get rid of this here, so I don't have to hard code it, and I can put it here. So basically what I am doing is I am incrementing this carrier waveform with a slope of FSW for every time step. So just all you have to do is take a paper and pencil and just work this out. This is how you would generate a sawtooth waveform. All right, so then what do? If carrier wave is greater than 1, carrier wave is equal to 0, because remember it has a peak of 1 and it has a time period and has a frequency of 1000 or a time of 1 by 1000. So therefore this carrier wave should not be greater than 1. If it is greater than 1, we have to reset it to 0. All right, now that we have done this, we don't have to do this anymore. You know what we can do? I can do something else. I can do what is called as a pulse width modulation. In pulse width modulation, I say mod signal is greater than carrier wave. So when the modulation signal is greater than the carrier wave, I turn on the switch. If it is not greater than the carrier wave, I turn off the switch. All right. Now in this lecture, I'm not going to talk about pulse width modulation because I want to talk about the actual control, how to write controls. I would suggest just Google search pulse width modulation if you want to know how this works. If you don't, just check out, just read any book of power electronics. This is pretty straightforward. Now here I'm going to set my modulation signal to be 0.5. Okay, so now that I have this, what do? This it won't work just as it is. You know why? There's a couple of problems. You see this equation? This expression has a plus equal to, and a plus equal to means this has to be a static variable. It cannot be as it is. So let me go back and define a static variable. Okay, this simulation has stopped. I can go back to main page, edit control, configure the control, and I will add a static variable. Now let me copy the static variable from here so that I don't make a syntax error. And initial value can be 0, no problem. So I should save this static variable, and let me come back here and check if there's anything else to be done. Modulation signal has been defined here, so that's okay, and I'll tell you how we redefine the modulation signal. And dt has been defined here as to be 10 nanoseconds. So let's go back and run this simulation. So let's go to view output, let's click on run. So it says simulation is running, but as always go to your command line and check if there is an error. There is no error, so it is indeed running. So now that we have this, let's go back and plot this value, output current plot. Let's see how it works, because now remember, we are switching this, we are controlling this switch at a much higher frequency than before. Before we weren't doing much. Well, it's hardly even started. So you see what has happened, the simulation has slowed down to some extent, and the simulation has slowed down for the simple reason that there is one control function which is now running at 10 nanoseconds. Okay, let's go back here and check. This is this one. This will generate time intervals at a time period 10 nanoseconds. So it's going to be 0, 10 nanoseconds, 20 nanoseconds, 30 nanoseconds, so on and so forth. Which means at each and every one of these time intervals, the simulation will execute this file. That is a guarantee that the circuit simulator gives. If you define a time interval, then at this time interval, the circuit simulator will run the simulation, guarantee. Okay. So I could come back here, well actually not here, I go back to the simulator and let me plot it again. I hope something has happened by now. Well, we have something. We have a waveform, but it's still not 10 minutes. Well, so in this manner, you can actually control your file. So I think at this point I am going to close this simulation because I think it will become a very long one again. But what I would like to tell you is that at this point, this simulation is probably not the best example of a control file. I gave this a simulation because it is the simplest simulation that contains every aspect of control and power electronics. So you see here. So one way to actually speed this process up is that I switch it off, and instead of having a frequency of 1000 Hertz, I have a frequency of 10 Hertz. So then we get back to the same old thing. Okay. Now typically this is not what you want to do, but like I said, this is not the usual simulation. So simulation is running. So in most cases, and later on I'll probably release another version. In the other version I'll try to talk about something like a buck converter or boost converter, or maybe even a DC to AC converter, because in that case control is more obvious. Usually you don't do this. You do not put a switch in the output of the load, because this switch, if it is, then this switch is just on or off. You don't do a pulse width modulation here. The only reason why I'm trying to show a pulse width modulation is to describe how a pulse width modulation can be performed using this controls. So I think it must have run for some amount of time, so we can plot it. Let me wait for just a little longer. And let me go back and check my output. Still it's too slow, it doesn't show you much. Well, eventually circuits actually, once as they grow big, circuits can actually run on for a long time. Matter of fact, some of my circuits run for days. So I guess simulation is that way. The bigger and more complex it gets, the more time it takes. So I'm just going to show you this one aspect. So let me plot it again. Let's hope it has run for a little longer. No, it hasn't. So now that this is done, I will go back. The idea was to show that it is possible. So now that you see the simulation is running much slower, one of the reasons for that is because we have reduced it. So we can always increase it back to the usual self. That is, we can make this, let's make this 100 microsecond. So now that it is 100 microsecond, it should be much faster. I can just stop this and run this again. Now before later, as it runs for a while, I will tell you a little about this. So this file, if you go through it, it describes the concept of a time event. Now when a control, there is, like I said, the control, there are several time events in the simulator. One of them is the integration time step, which is the simulation time step. That integration time instant is decided by the simulation time step. Besides that, every control file generates a control time event. All right, all these time events are collected together, and the lowest value becomes the next simulation, the next value of evaluation. So evaluation means all control files are on. Evaluation does not means that the simulation, that the differential equations for the circuit are not solved. It only means that the control functions are run. When are the differential equations for the circuit run? When a control function creates what is called as an event, or when, that is when an event occurs. So you read this file, when an event occurs, or when the time instant of the simulation itself is up. So let me come back here and let me just run this simulation. I think this is good enough. We should have some output. Plot this file. Yeah, and we are back to the same old thing. So you see, as time goes on, this becomes a turn on, turn off kind of thing. You see the output is changing, and as we turn it on more, it will become quite clear. So let me run it once more, and then I can wind up this lecture. Yeah, so you see what's happening. This is when the circuit, this is when the switch is on, and this is when the switch is off. All right, the switch is off, the output decreases. Switch is on, the output current is much higher. So in this way you can actually change, you can come up with all kinds of different controls. I mean, you can You can turn on the switch whenever you want. You can even have a pattern for turning it on and turning it off at a certain time. It's totally up to you. The only thing you need to understand is follow the rules that are necessary. For example, in this case, the plus equal to should give you an indication that this is a static variable. Alright. Similarly, define the time event and update the time event. Similarly, use when you are switching the output of this, when you are giving the output to this manner, define this as an output variable and connect this to the output that you want. So these are the things that you need to watch out for. And just out of curiosity, let's look at the output control file. Yeah, this is the output control file. So you see here, switch gate. Yeah, switch gate. So switch gate is the output variable that we defined for this switch, and you see it takes in the value of the output that is already there, and at the end it gives it back to the component. See, circuit components control values. This is a clear understanding. This is what it means. When you are defining a certain output variable and you're connecting it to a controllable element, you are feeding the output, the value of this variable, to the control value of this, to the control value of the circuit component. All right, that's what it means. So this is how it works, and let me just plot it once more. Actually, let me close this file so that I don't have a problem there. So I plot this file. And this is very clear. You see how clear it is now? This is when the switch is off. This is when the switch is on. This is when the switch is off. Again, the switch is on, and later on the switch is off. So this shows how pulse width modulation actually affects. All right. So this is the pulse width modulation. We chose a pulse width modulation. How much is the frequency? The frequency, gating control.pi, is 10 hertz. 10 hertz means this has a time period of 0.1 seconds. And if we come back here and we look at it, you see this has a time period of 0.1 seconds. You see, this is the time period when it is on, this is the time period it is off, and here is 0.1 seconds. So this is what it shows. It's off, it's on for half the time, it's off for half the time. So anyway, this I think should be clear enough about how we use circuits, and with this I'll wind up the control lecture series. This should be enough to get you going with your own control, and as time goes on I will release future videos where I describe more complex control and how you need help with more complex circuits. So as before, if you have any doubts, feel free to contact me either on email or on Messenger. It may be a while before I create my next video because it will have to be on a specific topic, so it may be next week. For now, thank you so much for watching, and I will see you again soon. Goodbye and have a nice weekend.